Howdy, everybody. Hope everything's going well with you, whenever you are. Um, Today was a fun day, and you know what? I say we just go ahead and get started with it. Day 24. I'm back at it. It's called Crossed Wires. If you're looking at the timestamp, I did take some time off, by the way. Just to be with family and holidays and stuff. So this one talks about how they you're given a device and it's got some wiring within it that you're trying to figure out what's going on. And they tell you the wiring has and or and XOR gates within it. And the idea is you're given some initial input wires and then those gates, either ands, ors, or XORs or ors, I guess, based on how I highlighted it. And they want you to, like, for part one at least, run the wire diagram and see what the Z wires output to. So the idea is you're going to do some work, and so for example, X0 and Y0 are 1 and 0, so the Z wire should be like 1 and 0 is 0, so that, right, it should be a 0 wire. Yeah, 0 appears on the Z0 wire. So that's the idea. What you're doing is you're just going to literally do these Boolean operators, or, bitwise operators on single bits, and output the results. And they give you a slightly more complicated example. So this one right here, they give you the example, and like you kind of go through the wires, right? So you find the values that are there. So for example, you have, I mean, this one's really weird looking, but you can imagine there's X's and Y's, and you figure out which ones you can do, and then you process them. And the way that it wants you to do is, like, it says at the end, find all the wires that are Z wires, turn it into binary, and then convert that into a number, right? So after you run this example, this larger example right here, and you look at all the Z wires, these are the bits that come out of the Z wires, and then you turn that into an integer, and you get 2024. And that's really it for part one. It's not really crazy. I mean, I think you probably have to think about how you might do this logic and how you might solve it. I actually looked at the problem, and I was like, oh well, there's only so many gates that you're running, right? I actually think in the original problem there's only like 300, but that doesn't even include the 100 or so or 50 or so input. There's like 90 inputs, so it's so small that, like, I felt like I could just brute force it. So just to be clear too, what these are is, like, you'll if you've done computer science, or like a computer, it's like computer systems course, or like a computer engineering style course, they talk to you about these gates. And the way to think about it is that these are like the diagrams for the gates. Is like you're given two wires, and if you and them together, it's the logical and of those two wires. So you can see here's a kind of table that it produces, right? It says, okay, well, if you give me two zeros, I'll give you a zero. If you give me a 0 and a 1, I'll give you a 0, a 1 and 0 and a 0. 1, 1 will give you a 1, right? So here's the AND gate. Here's the OR gate. You'll see these in diagrams a lot. I used Mermaid to diagram it. I'll show you in a second. But when we started, I actually didn't know what it was. But here's an AND, here's an OR, and here's an XOR gate. And they literally do the binary things. This is just like one, maybe two steps above. Like, if you think about the way your computer works, like one or two steps above actual transistors, right? Is like these gates are transistors, a series of transistors, such that if you give it an A and a B wire, it will output a Q wire, and that's how, and it does the AND part of it. And you can do lots of stuff with it. As you'll see in part two, you can do addition, right? But you can do all kinds of stuff. They've since, initially gates were just AND, OR, and XOR. I think quickly, though, you started to get some of these other gates like NAND gates, NOR gates, XNOR, and even more gates. NOT gates are also used a lot. Anyway, there's all these different gates that you can use. We're only using 3, though, and that's kind of a hint to part 2. We're only using AND, ORs, and XORs. So anyway, let's just, given all that information, the idea is you have all these logic gates. It's you have a wiring diagram is the way to think about it, and you want to like process that wiring diagram given some inputs. Okay, for part 1. So what does that look like in code? Maybe I can zoom this in a little bit so we can look at it. I tried to, especially as we got to part 2, tried to like really, add some structures and data structures to this to kind of help make it more readable. So I have a gate type with, my AND, OR, and XOR. And then I have a display for it. I think, I print it out when I'm doing the mermaid outputting, which you'll see in a minute. And I also I can pull the gate type from a string, right? So I impl from, so I can get that. And then I have a gate structure, right? Where I have the A and the B, which are the 2 inputs, and the Q, which is the output, and then the type of gate that it is, right? So I should be able to, based on these 4 things, say, okay, I can process this gate or whatever. Excuse me, I don't know why I'm yawning all of a sudden. So the interesting part here, I just use nom for parsing. You can see like all I'm literally doing is parsing the test input, right? So I say, okay, I'm going to get for the gates, which are down here, I'm going to get, the first value, the A value, and then I'm going to get one of these, and then I'm going to get the second input, and then I'm going to get the output that it should go to. And then based on that, I could just create a gate. Okay. I also have a run function that will tell me like, okay, how to, given these 2 values, run this gate. And that's just to kind of help me, which you'll see pretty soon. It's simply, hey, based on the type, do this. Then I don't have to worry about doing it later in the code. We'll ignore this stuff for now. I also keep track of the wires, right? So these are the initial wires. All the other wires default to null or empty, which is actually important when you're doing the wiring processing, right? Like the AND gate shouldn't trigger unless both of the inputs are ready, if that makes sense. But I do this. I do this mostly because I can then parse the wires on their own, which you can see here. Really, I'm just splitting it by the semicolon and getting the values. But then it also allows me to do some things like I can do a copied get where I say, hey, get the value of this wire. And if it's not there, I return none. Otherwise, I return the copied value. I also can say like, hey, get me these 2 inputs, right? So if you think about like when you're processing the gates, you want to be able to like only process gates that have both of their inputs ready. And so that's essentially what this does, right? It says, can I get A? Can I get B? If either of those fail, I return none. Otherwise, I return both of the values. I also have a setter. And then I have this with prefix, which I use to pull the Z wires out. I think you'll see in a minute. And then I just have the device, which contains, both the gates and the wires. I can parse them with these 2 values, right? So I just parse the wires first, which is this chunk. And then I parse the gates next, which is this chunk. You will see that I'm running in WSL here now. I had tried to do a bunch of stuff just in Windows land, but some of the libraries I really struggled to get working. And I'm sure it's just my unfamiliarity with Windows. So, okay, so what does your run function look like, right? Now that you have these gates and wires, how do you actually process them? Well, I literally just did it in a for loop. I just said, or a while loop, right? I'm going to loop through as long as something's changed in my wiring. I'm going to keep processing the thing, right? So what does that mean changed is if I've processed a gate and that's produced an output that I haven't seen before, then I should, say, hey, do this, process this again, right? Or set this up for processing. And then I'm literally just looping through all the gates and I'm saying, hey, is this gate's inputs ready? And if it is, run that gate and set change to true and just do that for all the gates. And if I've ever changed one of them, I do the loop over again. Okay. So I'm just doing it multiple times. The one additional check I have though, right, is if a wire's already triggered. It mentions somewhere in the text that the wires won't trigger again, right? So you could get these infinite loops where, or you could think this is what made it possible to do this is in a real computer, a gate might change, a wire might change, which updates the gate state, and then that gate should process again and change it. And so you can get these kind of loops until you get to an output. They specifically mention in the problem that that's not the case, is it's a directed gate. It's going all the way down. You can think of it as like a tree where you're just like slowly walking down until you get all the answers. So all I have to do is check, have I seen this one? Have I processed this one before? And if I have, I can skip over it. But otherwise, again, I'm just looping forever and I just say, hey, is this one ready? And have I processed it before? And if it's ready and I haven't, then I can add the wire, then I can run it and mark my change to true. And I just keep doing that over and over again. Is it the most efficient way to solve part 1? Probably not. Again, I kind of felt like, the input size is so small, let's just do it in this loop and see if part 2 causes a problem. You could potentially do like a graph traversal algorithm is the way you might think about it. It's like a BFS type thing of like where as you process a gate, so like what you could imagine is there's some list of gates that are ready to process, and once you process it, you go check and see, does that make any new gates available? And if it does, you add those to the list of ready to process, and you just slowly add those. So you could potentially reduce the number of, loops that you're doing here by doing that, because you're only looping through some kind of like unprocessed gates, and that would simplify it. It's probably something that I'd be interested in going back and doing for day 24. Again, though, I just did this while loop, and you can see it runs in microseconds, right? So we're not even in the milliseconds. Anyway, so how do I get our answer? Once everything's done, I just call this, get the Z as U size, which all I'm really doing is I'm saying, okay, find all the wires that have a Z with their prefix and sort them, right? We want to sort them in order so that we get the lowest one first, and then we just fold those values to get the I size. And basically what you do is you just shift one, and then if it's true, you increment it right here. At least that's how I did it. Again, I don't know if this is faster than anything. This is just the way that I did it. There's a potential just to like turn this into a string and then tell Rust, can you turn this binary string into an integer, and it would do that for you as well. This is just the way I did it because I was thinking in bytes at the time. Either of them probably don't matter because you're only running this one once, and so you just say, okay, well, this is really fast. I don't have to worry about the cost of it. So here's what it looks like for part 1. Literally, I just get the input string, I create the device, I run the device, I get the Z value output, and then I just return the results. And that's it. This was part 1. Again, is pretty straightforward if you think about it, especially if you're familiar with wiring diagrams. I feel like the hardest part may be figuring out how to do this part right here. And again, because you can literally just, I don't know, it's probably not brute forcing it, but it kind of is. You're literally just saying, which of these gates can I process them, and then just keep doing that until you've processed all the gates. There's nothing left to process, right? So, and that worked just fine for day 24. So there wasn't anything crazy about part 1 in my mind. Okay, so what changes in part 2? Part 2 says, Did I already get through it? Let's see. Oh, here it is. Okay, what it says is after you've looked at the device closely, you determine that the system you're simulating is trying to add two binary numbers. So again, like what I've talked about, you can use these gates to do addition. And so it's saying what it's doing is you have some X bits and some Y bits, and it's trying to add them together. And I mean that's like the part of part 2 that you kind of need to like, okay, now I need to know how these gates might work to get you to that solution. But essentially what it's saying is you take the X's and the Y's and it's going to do some addition, and then it's going to get you to the Z's, right? And those Z's will be the result of doing your addition. But what it says is the addition is not correct. There's the wires are actually misguided. They're not going in the right. Some of the wires are not going in the right place. And in fact, what it says is there are 4 specific pairs that are not in the right place. I'm not going to read all of this because it's just describing what's happening, and I'll talk about it in a second. But it's saying like there are 4 pairs of wires that have been switched. And what does that mean? Like at a high level, it says, I mean, if you look at this gate, you can see that X and Y's are ANDed together and producing a Z to the 5. I mean, that's not correct. This should be Z to the 0, right? So these 2 wires are switched, and then Z2 and Z1 are switched as well. So if you switch these and you switch those, now you've got these like 5 bits, right? Or these 5 ones correct. This example doesn't actually do addition. You're just ANDing these values together, which technically could work, but not for any complex addition. And so I'll show you how it works in a second. But just so you understand at a high level, that's what you're trying to solve is you've got this wiring diagram. You suspect that it's trying to do binary addition. It's trying to add 2 binary numbers. And but some of the wires are crossed, and you need to find 4 pairs of wires that are crossed and fix them so that you get the right value. And what it wants you to output is just the sorted array or the sorted list, comma separated list of bad wires. So you don't even have to solve the addition problem, mostly because if you know how adders work for these things, you just create your own and solve it, right? Or you could just take the bits. So what they're actually interested in is, which wires are bad. Okay. So in order to solve this, you actually need to know a little bit about how these adders work. And again, if you've done a computer engineering course, or maybe you've watched some videos on logic gates and how, the internals, the lower levels of how computers work, right? Computers are just abstractions upon abstractions upon abstractions upon abstractions until magically I'm here showing up on your screen wherever you're watching me. So the way that those work is you take these logic gates and you can join them together. I don't have Chrome up. By the way, I had a comment from one of the people that showed me this cool feature in Firefox that puts all my tabs on this side. Absolutely awesome. One of the coolest things I've seen in a long time. They used to have they have an add-on that does it. Here you can see my chicken scratch, by the way, of me trying to work this out by my head. Anyway, they used to have an add-on where you could see that you put the tabs on the right-hand side, but it was kind of ugly, if I'm honest, and it wasn't really helpful. It also was always kind of like this, and so it felt like it took up a lot of space. And so the way they have these new ones is really cool. I'm really enjoying it. So thank you for your comments. Again, I love reading your comments. I love seeing your answers to the solutions. It really, the goal is to expand our minds, right? And so you guys helping me expand mine is also just as cool. So think about what you have to do with addition, right? I probably should have set all this stuff up before, huh? So you're doing some kind of addition, and a very simple addition is you say, okay, well, I could have 2 zeros, right? So I have A and B and then my output, right? And 2 zeros, that should just be a 0. I could have a 1 and a 0, and I add those together, that should give me a 1. I could also have a 0 and a 1, I add those together, that gives me a 1. And then if I add 2 1s, that gives me a 10 in binary, a 1 0 in binary, right? Okay, that's simple addition. You imagine if this is x0 0 and this is y0 0, these would be your values. The one struggle you get to is right here, though, right? Is you say, oh, well, how do I do this? And this is where when you first start, they talk to you about an addition method called ripple addition with binaries. Like you end up with, you have all these values, right? And you do this math and it gets you to right here. And now you have this like extra value. And they call it a carry bit, and you like, it's a ripple carry. Did I say that wrong? You do ripple carry addition. You want to feed this into the next addition you do, right? It's not just sufficient to just like say, oh, that my y00 is equal to 10. That won't work, right? Because you want to take this and push it into the other one, right? So now you have something slightly more complex when you're doing your addition. You have A and you have B, and then you have this like carry that is coming in, right? You have this carry bit that's coming in, and then you're going to have your output as well as some carry out, right? Some value that you might carry out, a value that needs to be used with the next bit. And you're going to just do that over and over again until you get done, and then you'll have one additional bit. You'll have one additional carry bit at the end that may be left over. So I'm not going to do all of these, but you can imagine like 0 0 0 should produce 0 0, and you get far enough down that you're like, okay, well, again, I won't do all those, but you get something like 1 1 1. These all carry in to produce 11, right? So the output should be 1 and 1, right? And you just do this. You do this same math, but now you're also tracking this carry in and this carry out. And these are called, so when you're doing a ripple carry, this is called a half adder, and this one's called a full adder with carry, right? And they call it full is because you're working with the carry in and the carry out. And they show you how it works. And that you can actually go, if you go to this adder thing, it will show you how it works. So here's a half adder in action. You can see you get 2 values. And the way that you do that is you get the S or the Q by doing an XOR. So you XOR the 2 values. And then you get the carry bit by doing an AND of the 2 values. Okay? So why does that work? Well, think about what an XOR does is it produces a 1 if exactly one of them are 1, right? And that's actually what you want, right? It produces a 1 if exactly one of them are 1, right? So that's this part right here. That's this side, right? So in both cases, we want these to be zeros if they're both zeros or they're both 1s. But if they're 1, if either of them are 1, we want to produce a 1 there. And then we do an AND for the carry bit because we, again, think about these 2 values. We want to produce whatever the carry value is, this value right here. We want to produce this value right here. So you can imagine doing an AND here, a 1 1, and here will produce a 1, but all these others produce zeros, right? Because none of them are both turned on. They're both they're all false, right? The reality is if you think about the carry bit here, it's all zeros. And so that's how you get to a value like this, right? And that's the half adder. So this half adder produces an output Q and some carry bit for your thing, okay? And again, this is used in like a ripple carry. There's other half adders you can use using different types of gates to get you the same stuff that are actually faster. But for all intents and purposes, half adder is perfect, right? Now, this will only happen if you think about the binary addition you're doing. This will only happen once, the very first time, right? the very first time you're running the program, you're going to want to do this half adder, but now from now on, you're going to have some carry bit, right? I don't know. Do you guys remember doing like multiplication or addition this way? Like it was a 746 plus 829 or whatever. Essentially what you're doing is this, right? Is one's left over. And like this is the carry, and these are the A's and these are the B's. And so you're each of these are going to have some kind of carry bit, right? In this case it's 0, right, to get to here. But then there's going to be one left over at the end, right? So this is, if I did my math, it looks like this. This is like your final carry bit, and like these are all your Y's, right? So, or your Z's in this cases. But that first time, you don't have a carry bit up here, right? There's no carry bit. So you can just do the basic addition, which is this side. And then every other time you need to do this like more complicated addition, which is right here, okay? And so what is that more complicated addition? Here's what it looks like. It's actually not much crazier. Again, we want to produce the output of this should be should only be set if one but not both of these are set, if that makes sense. But this time there's 3 of them, and so you just need to XOR over 3 values to get the solution, right? So the 3 XORs of this will give you the solution, and then you just need to do an AND of these 2 and an AND of the results of the XORing of this one and this carry bit right here, and that. So that's the first one that I just talked about, and then that's the second one. You do an AND of those 2, and then you OR them together, and that's going to get you your carry bit. And I won't go into the logic of this. It's a little bit more complicated. I actually drew it out here in Mermaid. So you can see here's what the half adder looks like. You basically take the 2 input bits, you XOR them together, and that gives you your initial one. You take the 2 input bits, and you AND them together, and that gives you your carry bit. Again, this one's more complicated, the full adder, but it has the same effect, right? Is like you're trying to get to your output bit down here, and the way you do that is you XOR these 2, and then you do an XOR of your incoming carry bit with the result of this XOR right here, right? So you have some carry bit and the XOR of these, and that takes you down to the Z value. And again, why are you XORing is just like, it's the same reason with the half adder. You're really only interested in like the first bit. And so doing that XOR is you're saying, hey, I only want to, I'm only going to turn on or off this bit if only one of them are 1. I'm only going to turn on the bit if one of them, exactly one of them are 1. And so that has the case of doing this XOR twice, has the case of, you know, checking all 3 of these and saying, I only want all 3 of these to be set. Or if both of them are set, the XOR of this one will go to 0 and this one will go to 1. And now you get a 1 here again, because remember all 3 of them together, if like that would turn into it. Did I say this wrong? If these are both 0, the XOR produces a 0 and this one's a 1, you now get a 1 down here, right? But if all 3 of them are turned on, that's going to turn this XOR is going to become a 0, and this one is a 1, and so now that gives you a 1, right? And that's where you get that the last one that we were looking at right here, right? This one right here, it turns it on, right? So again, this is just Boolean math if you've done it before. And again, to get the carry bit, instead of using XORs, you're now using ANDs. And the idea is you're going to AND these 2 together, and then you're going to AND these 2 together, and then you're going to OR the results of those 2 ANDs. And this has the effect, again, what you're trying to figure out is the carry bit. And the reason the ANDs work here is because you're like checking that second bit and seeing that would adding these bits together give me a carry, right? And so that's why you're doing the ANDs there. And if either of these give you a carry, the OR is what turns it on, right? Is the way to think about it. So if this one carries so if this one produces a 10, like if it's 1 1 and this produces a am I doing that right? This is 1 and 1, anding them together produces a 1. So this is 1. Regardless of what this is, you know you're going to carry, right? The same thing right here as you're anding these two together. If both of these are a 1, you know you're going to carry, right? And in both cases, you're going to carry. Again, remember, like this left-hand side is dealing with like the first bit, and the right hand is dealing with the second. And that's why this works, is you're really only worried about that specific bit, okay? Hopefully I explained that stuff okay. I felt like I went through it pretty far. Anyway, the whole point of this is you kind of have to understand this so that you can look at the diagram and see what's going on and figure out what's wrong. So what it's telling you in the problem is it's actually saying some of these wires are crossed, right? So it's saying, I don't know if this is a good example, but maybe this C0 goes to this OR, and this V2 goes to this AND right here, right? And so now the wires are crossed, and it's going to potentially produce different results, right? Or this V1 and this V2 are crossed, right? So this one is going to this OR, and this one's going to this XOR or something like that. So now this wire and this wire are crossed, and so now you're not getting the correct results, right? So that can be a little complicated, especially for a big thing. But the idea is maybe the way to think about it at a high level is you're going to look at your diagram and expect the first grid to look like this, the first bit of addition to do this, and then all other bits of addition to do this. And then this last carry bit would be the final Z wire, which is like the additional Z output. But that's what you're looking for. The goal is, can I look for this in my input and look for this in my input, and anytime I don't see it, I can say, oh, there's a bad wire there. So here is the actual, I did it in Mermaid, and to be honest, it looks pretty ugly. I think it's just because I didn't do a good job of like ordering the stuff in Mermaid for the output. But you can actually see, for example, right here, you can see the initial Y, X0, Y0 being XORed together to get the Z bit, right? You get the Z right here, and then you AND it to get this carry bit. So it's called QVN, but this is the initial carry bit. And you can see it's actually used to produce the Z1 bit, right? So the next bit that you're trying to produce from X and Y, you XOR them together, and then you XOR that result with the original carry bit to get the Z1 bit. And then you take that and you AND it with the results of the XOR and the results of the AND of these two and OR them together to get your next carry bit. So this is the second carry bit. And now you can see here's X2 and Y2 being ANDed together, and then ANDed together with this OR, like this carry bit, to get the next carry bit. But you can also see that this output is these two are being XORed and then being XORed with this one to get the Z2. So I explained that. It's a little complicated, but you can, and it doesn't look great, I'll admit. So if you had a better way of outputting this, I would actually be interested in seeing it. But you can actually see, oh yes, it's definitely doing a ripple carry adder. It's doing what I just described. And I had to go through that work. I did that initially. In fact, you can see it in my code. The very first thing I do after I'm going through this is like, okay, I'm going to print out my own half adder so I can see what it looks like. Print out my full adder so I can see what it looks like. And then I'm going to print out my actual input program, right? The input of my code, and see what it looks like into this circuit diagram. And then I used Mermaid to like print it out and display it. So here's my Mermaid function if you're interested. It's not really interesting. I just gave some class definitions for the different values. And basically I start with my X and XYZ bits, the start bits, the 0 bits. And I just slowly keep adding bits that are the outputs of those gates that are ready or that I've printed get added to the queue. and I basically just print this out for each gate. Excuse me, for each gate and link them. So that's all that I'm doing for my mermaid. But I mean, there are other ways to do it. I suspected at the time that it was going to be a ripple adder just because it was doing XORs, ANDs, and ORs. But I wanted to verify because I didn't remember a lot about my computer engineering classes. And so that's what got me to printing these and looking at them. So now all you have to do is find where it's bad. You could potentially trace these diagrams and update these values, right? Imagine looking at this and saying, oh, well, this is maybe up here. This is carry 0, so I should expect that to be XORed with the results of this to get to the answer. And you could do it by hand. I suspect that there are people who did it by hand, and I think that's just fine. You print it out like this, do it by hand. There's only 4 pairs, so you're only going to find like 8 errors. There is a lot, right? But there's only 8 of them. And so I always tell people that, like, you'd be surprised at how efficient our eyes are at, like, seeing seeing problems, seeing things out of scope, where it's harder for like a computer to see that without like some effort. And you'll see I do it programmatically, but it takes some effort. Anyway, the whole point is you can kind of see how it works and the processing it's doing. And if you traced it, you could find the errors. And I think there's one of these errors is down here, because when I was looking at it, I think these two are switched. Is that right? When I was looking at it, I was like, oh, there are some, Z8 is switched with, is it that this should be the carry and, yes, because you're anding and oring, so this should be like the carry, and the XOR, so Z8's XOR, this one, so VVR and Z08 are switched. Is that right? Yeah, these two are switched. You can kind of see that, again, I apologize for the mermaid, but you can see like this VVR is being part of an XOR, and that we know that the two XORs, right, if you look back at these adders, the XORs always produce the output bits, right? These two XORs always produce the output bits. So you would expect anytime you see an XOR is you get an output bit. And so you see these two, an XOR here, and then an XOR here, and that produces this. That doesn't make any sense, right? The X and Y nines that do an XOR and an XOR to get here are correct though, right? So anyway, that should be assigned to you that something's wrong. Maybe I didn't see that quite right, but I think it is these two that are switched. Anyway, the point is, you really just have to loop through and ask yourself, does this one, does my current adder look like this one? And does my initial one look like this one? And that's all you're really doing in code. So how do we do that? You can see here I'm going to track my bad wires, and then I'm going to go through all the input XOR gates. So those are this initial gate right here, right? Essentially, I'm saying, what are all the gates that have an X0 or a Y0 as its input gate? And so that's this right here, this initial XOR right here, or this initial XOR right here. And I just need to check. I say, I use a match statement here, but I say, is it a half adder input, meaning it's the initial one, and is the gate 0, 0? And if it is a half adder and it's 0, 0, so those are both true, then we're good, right? If they're both false, meaning it's not Z0, 0, and it's not a half adder input, they're both false, that's also good, right? It means we've got a full adder and it's outputting to some other wire than Z0, 0. And so that's good. Otherwise, either of these two means that something's wrong, and so we want to push those bad wires, right? We would say, oh, those two are incorrect, so we need to spit those out as quote unquote bad wires. Any other XOR gate that is in there should not have an output gate, right? So these are all yeah, so if you imagine, like, let's see, the any other XOR gate right here. So how do I describe this? This one does have an output, right? So this one does have an output, but this one does not. It should not output to a Z wire. It's only the second XOR that outputs to the Z wire. So what that next check is we're saying, hey, if these two XOR to some Z wire, that's not correct. And so we know that one's a bad one. And that's basically what this check is carrying to. Why? Because in the half adder case, that's okay. And that's this case right here. But in all other cases, that's not okay. So we want to add that bad wire to our list. Okay. So that's basically essentially what we've done is we've checked all of these XOR gates. Are they valid? And we've said, okay, well, we expect to have these two as inputs and this one as an output. Except in the very first case, we expect it to go out to a Z wire. And so that's the first check we've done. So now let's check all the intermediate XOR gates, right? And so that is this gate right here. And you'll notice there's an expectation that it should be a carry wire should come in, and it should be the other part of it should be an XOR from the previous. And we'll solve that in a second. But the first thing to keep in mind is this second XOR should output to a Z gate, right? Any other Z should output to it. I apologize for putting Z00 there because I just did this as like an initializer, but technically this one is Z00, and then these ones should be Z01, and so on and so forth. But again, I'm basically just checking all the immediate gates, and I say, if any of them is not an output, then that one has to be a bad wire too, right? So if I'm doing this and I don't get a Z, right? I'm doing this XOR and I don't get a Z as the output, then that one's got to be bad as well, right? So that's what this check is, okay? What is my next check? I want to check all the output gates. So basically what this is any gate that spits out a Z, I want to check all those now. And I want to make sure, you'll see what I do here is I basically say, so for each, I'm going to look, and for all of the output gates, but the last one, they should be a result of an XOR, except for the last one. The last one should be an OR, right? You should, and maybe I can even show it here. I can go all the way down to the bottom. The last one is just an OR, and why is that? Is because this would normally be the carry wire, where you do an and, and then you OR them together. So this would normally be like another variable. It would be your carry bit, but in this case, it's not. So I just need to check for that case. And essentially what I'm saying is I should expect all of the outputs to come from those correct places. And so that's what I do here. I need to know what the last Z wire is. So that's what I do to get the last Z wire. And then I basically just go through all those output gates and say, hey, if I'm at the last Z wire and it's not an OR, then I know something's wrong. It turns out most of these checks that I was doing were not working. And I will give you a hint. Not a hint, but a heads up. I don't know that my solution solves all the problems because I basically just went until I got 8. It's the way to think about it. And so I was just trying all these cases. I'm like, okay, well, what if these ones are switched? What if these ones are switched? And eventually you get to the point where, oh, now I found all the switches. But I don't think it solves it in the general case. Maybe it solves it for all the inputs, but I don't know if it solves it for the general cases. Okay, so what I do is I say, look at all the output gates. If it's the last one, I expect there to be an OR. Otherwise, it's a bad wire. Otherwise, I expect it to be an XOR, and if it's not, it's a bad wire. Again, that's like me checking either this one or this one, right? So this should be coming from an XOR, and this one should be coming from an OR. So what have I tested at this point? Essentially, I've tested like this XOR and this XOR coming from like this way and coming from down here and this way, right? So the rest gets a little bit more complicated because now I need to like check if these like internal values are consistent is maybe the easiest way to think about it. Like, is the result of this XOR right here used in this AND is essentially like what I'm checking here. And at the same time, is this OR using the result of this and this and right here, right? And I'm using this actually gets you to the answer, but again, it's kind of a weird one. Basically, I loop through all the XORs again, and I just double check to make if I've already found a failure or I'm in a half adder, I know these aren't the case. But now I'm going to compare, I'm going to find any intermediate gates that have the output of my input gate as its input. What is that saying? So this gate produces this output, and I want to find any of these gates that have essentially I'm trying to find this and right here, right? So I want to find where this one of these value where the output of this gate is equal to the input of this gate. Okay, so that's what I'm checking for right here. And if I don't find one, I know I have a failure, right? Something's wrong here and I need to fix it. Okay, and the way that I fixed it initially was I hoped and prayed that there was like some internal consistency errors. And so that's why I'm just kind of keeping a list of like the ones that I need to check further. Any case that maybe the way to think about it is anytime I found this and it does look correct, there's no reason for me to like check this part of it further because now I've like checked this right here. Like essentially I've checked all this thing right here, and there's no reason for me to like check, at least at this point, this stuff over here, right? But you'll see me do that in a second. But anyway, the point is if I find some bad wire, I know that something's wrong with it. And so I'm going to add it to my checklist. And these are like gates. These are gates where something is off about them. And so I know something needs to be swapped with them. And my goal is to kind of try and find some gate in here that I can swap it with internally. And that's what this check is doing down here. Basically, I'm saying these intermediate gates, so for all of the ones that were failed in here, right, I'm going to go look and see if I can't find within the gate the one that it should be switched with. Again, this does not work in the general case because you could imagine. I mean, I guess I didn't look. I think it, yeah, like the idea is there's like some internal switching going on here. Like these two are switched. The Z28 is probably switched with one of these. I actually don't know what it is. The Z39 is switched with one of these. And then there's two of these internal gates that are like internal variables that are switched. That was my thinking, is maybe they're just switching internally. And it turns out that's the case for my problem input, is there's just internal switches that are off. So just to reiterate what I'm saying here is my initial checks were, okay, well, what if this one's wrong, like this input is wrong, maybe it's just switched with, maybe this is switched with this, or this is switched with this, or this is switched with this, right? There's just some switch here. I just need to find which of those is the case, and then I can add it to my list. I removed all the code that was doing this, but I was initially just, I literally just started right here and said, okay, how many of these, no, it wasn't even here. I was just like, okay, I'm going to do this. How many of these are wrong? And I would literally print it. How many of these are wrong? And it was, I think initially it was 0. And then I was like, hey, okay, well, how many of these are wrong? And it was like, oh, there's 2 of those that are wrong. And then I was like, oh, how many of these are wrong? And then it was like up to 7 or something like that, or 5. I don't remember. And so I just kept doing that until I got to 8. So again, fair warning, this may not solve your input. I honestly don't know. Anyway, so I know that there's some gates that are bad, and my hope is, can I find a switch for those gates, right? Can I find something that I need to switch them with? And that's all this is doing, right? Is I'm just looking through the gate. I need to extract the A variable here because I need I use it right here to get what I expect the output to be. And so I use this destructuring in Rust. I asked Claude about this, and it was like, oh, you can do this destructuring. I probably, after Claude said you can do this destructuring, I was like, oh, that's cool. I wonder if I could do destructuring up here in different ways. You can see I use gate Q a lot up here. It's almost not worth it though, right? At least, well, you do use it some other places. Anyway, the point, actually, I don't think you do. Oh, I know what it was. At the time, I was also using Q as well. Right down here. Yeah, right here. Oh, I still use it. That's hilarious. So you could use it. Oh, no. That's referring to this gate. Never mind. I don't remember. I did a lot of reformatting to figure out how to get this to work, but you can probably get, in fact, we can probably just get rid of it right now because it looks kind of ugly, the destructuring. Please give me the right answer. It does it. Okay, good. Okay, so what am I doing? Basically, I'm just saying, like, okay, I know I have, because I've done like this on the input XOR gates with the immediate XOR gates, I know that the second XOR gate should output to some expected value. And so that's what I'm just checking out right here is like, what do I expect it to output to, right? And so I'm going to go through all the immediate gates and find out the one that I expect this gate to spit out to. I know I'm expecting this to spit out to one of these wires because it's an XOR gate. It's this gate. So I know I'm expecting it to spit out to this. So I'm going to go and find that. Right? Find that intermediate gate. And then I'm going to go through all the devices and find all the OR gates where the output of that gate is the output of that gate is one of these input are the inputs of this gate right here, right? So what is that? So that so describe it one more time. This is the intermediate gate. That's like this gate right here, and that's these two values right here, right? So I want to find the the OR, right? Where is that right? Am I saying this right? I want to find where the gate type is OR and the output is this. It's not really showing you this, but it's this is not. Oh, maybe I need to go here and show it because what it's actually doing is scroll to the top here. Okay, so this here is the first full adder right here, the X1 and the Y1. You can see like I'm doing, you're doing the XORs and the ANDs, and you do this OR to get you the next carry bit. So it's like this OR right here is the one I'm interested in, and I'm so I want to know where these two came from and this OR came from, and are they associated with the this XOR right here, I think is what I'm trying to describe. I feel like I've lost. It might be easier. This carry bit is the result of an XOR, right? The initial carry bit isn't because it's a half adder. But this carry bit right here is the result of an OR, right? So like I'm checking this OR and making sure it's consistent with itself, with the bits above it, is if that makes sense. And that's what this check is doing. And I basically just say, okay, I want to find all the gates where it's an OR gate and its output is the input of one of these intermediate gates, right? So the OR gate is this OR gate. I mean, you can think about this part being put up here. I'm looking for this OR gate that that produces one of these two values. What I'm essentially looking for is this carry one, right? Is the way to think about it. Again, if I described it. I feel like I'm not describing it very well. My mind was going through this all crazily. I felt like a madman wiring all the gates together. But then I can basically just check and say, hey, if my intermediate OR gate is not the output of this queue, or the other one is not the output of the queue, then those must be bad wires, right? And this may be a bug here. It produced the right answer, and so I stopped. But I actually think you only are worried about one of these being wrong. Like, the case that it wouldn't work is if like this one was crossed with this one and this one was crossed with this one. They're like double crossed. Like, was the case that I was trying to think for, but I actually don't think this solves that. So anyway, that actually got me to the answer. So again, how do I feel about today is maybe the way to think about it. So here's the answer, by the way. Here's the answer. You do it. You can see the whole problem runs really fast, right? Especially part 2, because I'm literally just checking, does the state of this gate, or does the state of this adder look like this right here? And I was just going through and finding them. You can see I didn't even I don't think I checked over to here yet, right? Like, I didn't check these V2 or V3s. I was just like checking along this way, and I got to 8, and so I stopped. This is definitely a day that I feel like I'd like to go back to. And there's a couple reasons I'd like to go back to it. Again, I just got to 8 and I stopped. I kind of ran out of time. I got to 8 and I stopped. But I don't think it fully handles cases where, like, okay, well, what if this carry adder is actually the carry adder from like 2 behind it or whatever, right? So it's like way out of the way. I had to think about it. Maybe it does find those. I don't think it does. And originally I thought about, like, how would you find that case, right? And the way you would do it is you would need to just know what the previous adder's output was, like the previous adder's carry bit is, and if that one's okay, then you're okay. I mean, I kind of do that right here. Like, that's what this is checking for right here. It's checking to make sure that but it's only checking to say, is like, does the intermediate gate come from the XOR of, is there a device that produces that XOR? Sorry, how do I say this? Is there a gate, an OR gate, that produces a value that can be XORed to one of these intermediate gates to get you to what I expect it to be? And my inkling was, if it's not, I now need to check further and say, like, well, where does this XOR come from? Is it like, is this XOR intended to be, is this OR gate that produces the carry bit the previous one of this one, right? So you'd have like a previous expected, and you go check it. Again, I didn't actually have to do that. So I do feel in some ways I kind of cheated my way to a solution, but it actually took me a while to get here. And so once I got the solution, I stopped. Again, I probably spent, I don't know, the better part of 4 to 6 hours on this thing. And a lot of it was just trying to, once I found the answer, I did spend about an hour trying to clean up the code. And so these things didn't used to look like this, but I tried to clean it. I added a bunch of these has inputs and stuff like that. Oh, I don't know if I mentioned that. I added a bunch of these to make the code like more concise and clear. There were a lot of places where I was doing this check, or especially this check, to say, is it the input? And it, like right here, these like things where I'm collecting these values. You might ask, why do you collect them? And it's because I actually realized, like, later in the game, I'm using them later down here again. And I had, right here's the input XOR gates. I'm doing it again. So I collected them up here just to make it more concise and make more sense. But there's a lot of crazy code, and I actually think that was part of the reason why I was struggling. It took me 4 to 6 hours, is I wasn't using some of these things right here. And so just as a word to the wise, is like, it was a reminder to me of actually writing clean code and data structures and doing some level of abstraction can help make your code look more readable. I may not have explained this very well. I hope I did. But the point of it is like once you start cleaning up your code and start naming things correctly, it actually doesn't look too bad. You can see I wish I had reset these because this one is the I should have called it something like the the carry, or sorry, the output of the intermediate output from the carry bit or something like that. I don't know. And then this one is like the or, I called it O, but it's like the or up here, which is this one right here, where this carry matches this one right here, right? So I could have renamed these and it would have made more sense, I think. Anyway, I did use A and B because it's common to use A and B in these things. You see it a lot right here, A, B, and Q. Even though it's X, Y, and Z in the thing, A, B, and C for the carry is very common. They use S here. I guess S is probably more common for like these the adder things. You call them S would be my guess. But anyway, hopefully all of that makes sense. It was a weird day. I feel like I got to the answer. Is it the perfect solution? No. Is it a day I'd like to revisit? Almost certainly yes. So I have plans to revisit these days, and this is one that I think I'll revisit. Anything else that I want to talk about? I don't think so. So let's just go to Reddit really quick and see. I'm doing this way late, so I may not. Day 24 solutions 2024. Will I be able to get them? I just want to look at a couple people, see if anyone. My guess is some people did it by hand. Oh, renaming the wires. That would have been a good idea. Imagine like I'm renaming them. I guess I didn't need to go. Like imagine I'm renaming this like what's a good one? This one carry 0. It's really easy for me to say, oh, does the carry 0 come from the X and Y's? That's actually a really good idea. Oh, you can even name them like this. So you say like, oh, this is the and of 14, and you want to do the or of the and of 14 with this. You keep renaming them, and eventually you get to like some really obvious names. Carry intermediate 2. Yeah, this is a good idea too. So this is definitely something I probably should have done. I'll keep that in my back pocket for renaming them. Let's just see what they did here really quick if we can figure out. If the operation is an XOR and it's an input, okay, so it looks like they are doing some similar things. And it's an input, and the initial out is a 0 or a Z. Why would that be incorrect? Am I just reading the opposite? Because it actually is an XOR, right? Oh, it's talking maybe that he's ignoring the half adder and he's saying like this and this. If it ever produces a Z, it's the incorrect one. Okay, that's probably what they're saying there, would be my guess. So they must do something to say, is it the half adder? If his input and it's an and an XOR. Oh, it's not an and, or it's not an XOR. Oh, okay. Oh, that's interesting. So they are doing the checks. And these ones may actually make more sense than the ones that I did, right? Like essentially what they're checking is they're saying, okay, check to make sure that these two map to an and that this one, is that right? They're saying like uh check to make sure that these two map to an and an XOR, right? Is essentially what they're saying there. So this one may be more readable than what I did. I was really just thinking about, okay, we're just going to try things one at a time. They're doing it all in one loop, right? You're basically going through each of the gates and checking to make sure that that gate is consistent with what you expect. And you could do that too, right? Is because the way, like, why can you do that? Is because you can kind of work your way up the gate tree. I keep not being able to find this because I usually have it in my Chrome thing. But like, imagine you're checking this gate. It's an AND gate. You can tell if it's the input one if it has one of these as input. Otherwise, you expect it to be this one that's linked to the OR, and so you kind of work your way through it that way, right? There's only, if you think about it, there's an XOR, two ANDs, and an OR. And so you can kind of say like, oh, well, I can determine if it's the first AND by these X's and Y's, or if it's an intermediate AND or OR by if it's not one of these inputs. And then you can say to yourself, oh, can I do some checks to see if they're consistent? And this actually looks like it's more concise than mine. So I may try and look at theirs. But you can see, hopefully, in my terrible code, you can see that I was essentially trying to do what they're doing. I was just doing it in like multiple for loops, and I was doing it in maybe a less more concise way than this. But that's all they're doing, right? Is they're essentially saying, are all these values correct? And if they're not, then you add it to like the naughty list. And once you've gotten 8 naughties, you're done, is maybe the way to think about it. Rewrote it to solve it programmatically. Okay, so maybe this person initially solved it by hand. And again, I think this is definitely one you can do like if you kind of spit it out. Let's see. I did part 1 using functional. Part 2, I can't tell. Part 2 finally. Okay, brute force. This is actually interesting. You could find, so again, because you know it's like a ripple adder, a ripple carry adder, I think is what they call it. You could slowly do that. You can find the solution, right? You know what the bits should be in the final output. And so you can say like, okay, produce the first bit. Is it correct? Produce the second bit. Is it correct? Produce the third. Is it? And eventually you get to one where it's incorrect. And you can, okay, you say, oh, I think mine was, what was it? Z8 is correct or incorrect. You say, oh, Z8's not the right value. So now I need to like try and, there's something wrong in either the adder for Z8 or the carry that's produced from Z8 in Z7. Can I like switch those around until I get the right answer? That's an interesting way to do it. I think that's a cool idea. How many lines is mine? People are talking about how long theirs were. 300 is quite a bit. The rest of this is just me printing it out, so you get to like 500. Oh, I have a bunch of other. You can see here I was doing a bunch of stuff beforehand, like these checks and things like that. I slowly cleaned it up a little bit, but anyway, yeah, 420 lines if you include the stuff. About 300 lines. Again, most of that is, I don't know, 192 is like the setup stuff up here, which is still part of it, but it's, I mean, it's pretty big. This solution was pretty big because you're doing like a lot of checks, right? rendering it in Graphiz and doing spot the difference troubleshooting. I was already familiar with this circuit. Does Graphiz make it look better? Oh, here's the Graphiz. I wonder if Graphiz would show up better than Mermaid. It kind of makes me want to... DAT24. I want to see if there's any... return statement in my function. I kind of want to find some Graphizes. Oh, theirs looks much better. So they say they use Mermaid as well. Ooh, I could have used different things for the inputs and stuff. How did they get theirs to look? Much better than mine. Mine really sucked. So I can show you essentially. Oh, I did show you what I do to my Mermaid, right? I essentially just like kind of start with the X's and Y's that I know about and slowly add their outputs to the list and push those in there. So I kind of want to find this person's code and see how they did it. It says they haven't checked it in. Bummer. I would actually like to see how they did it because you can see mine does not look this good, right? And so you see these very like here's the normal adder where you're taking this is like the carry and you're doing the XOR XOR to get to the actual value, and then you're doing the and ors to get to the next one to get to the next carry. And then you see this one is normal because it doesn't look right. Although this does suggest that my intuition was correct, is like that you just had how do I say this? My initial thought was maybe just the internal wiring of a single adder is crossed. And so maybe that was the case for all the inputs. And if that's the case, then mine probably solves all of the inputs, though not the general case. That C solution that we found looks like it's more inclined to solve all the cases. C++, this one. It looks like they're literally looking for all the cases. And then it's looking for like this. This is like the half adder case. Yeah. Okay. Yeah. So here you can see that this first part looks weird because it's the half adder, and so you don't have all the stuff. But you can kind of go through and you start to see, oh, those are switched. Okay, so this does lead me to believe that, yeah, my intuition was correct, and it's internally inconsistent. Because you're like, oh, these two are switched. Oh, these two are switched. This one is a mess. But my guess is it's just because, like, of the switching, it looks funny like this. And then you fix it, and now it all looks right, and you get the thing. Interesting Network X. I would like to see their code of how they did this. Because one of the things, my thought was, can you visualize this? There's been days before where it's much easier to like visualize the solution and just see what's wrong with them. And this would be a clear, oh, these two are switched. You know, this one is switched with this one, and this one is switched with this one, right? Something along those lines. These two are switched. I think this one has like, so you've got 1, 2, 3, 4, 5, 6, 7, 8. It looks like there's like 3 switches in there. Would be my guess. It would be if I got Mermaid to output like this or the previous one we saw before. (14 times 9 instead of 9 to the 14. Okay, yeah. There's only 14 processing blocks. Oh, this is the wrong year. I was like, that's not the case. There's like 44, right? There's 44 blocks. It was close though. Like you think, if you're saying to yourself, I'm just gonna try and fix the ones again. There's only 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 gates within a single adder, and potentially, but there's 1, 2, 1, 2. Well, you can check this one by hand, and you can check this output by hand. So you really just 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's like 5 ways for you to rearrange this. So like 5 factorial is only 25. That's not a lot, right? It's like how many ways can you rearrange these combinations to get the right output? That may not actually be too bad of a solution, even though it was for the wrong day. My codes, finding each possible individual swap and seeing the effect of it on the initial result. It does run pretty fast, and if you could get it to run pretty fast, you could potentially just do swaps. Yeah, this is essentially what I was doing. It happens in less than 100 milliseconds. But I'd like to verify it by running the corrected gate arrangements. That's true. Mine doesn't tell you which ones are out of place, just that there was 8. Again, my goal was a little silly to begin with. My thought was, can I work my way up to a generalized solution, and eventually I would get there. But I hit 8 and I stopped. So again, this part down here may not actually be correct. I'll have to think this through more, and this is definitely a day I'll come back to. But I don't actually know which signals were crossed. My initial implementation, I don't think I have it down here, was along the lines of, can I just check the half adder and make sure its inputs are X0, Y0, and its outputs are Z0? And can I find those ones? And then this is where I started doing like the full adder stuff, is where I said, can I go through each of them and I know what the previous carry bit is? Can I do it? Can I check that full adder with what I expect the X and Y's to be and the Z's to be? And here's my carry adder. And so it's going to give me the Z value and the carry adder. I can check all those. I didn't actually end up using this because this check full adder it felt kind of complicated. As I was doing it, I was saying to the way that I was initially solving it was along the lines of, okay, I have this, I know what I expect this to be, and I know that I know what this is as well, because I've seen it before from the previous full adder. And my initial thinking was along the lines of, okay, find this XOR and see what this produces, and then make sure that I can find a gate that has this, and this is its input, and this is its output. And then make sure I find this and to get V2, and make sure that it produces the x the and of these two produces this value, which produces this gate and this thing. It's kind of like a top down approach of saying, are all these correct? The struggle I had was like, if any of them were ever wrong, like say this was this was actually V2. Well, I didn't know it wasn't V2. How do I say this? I would not find this right. This one produced this right here. How do I say this? This one is an XORs to here, which XORs to here, right? And I would know that this XOR should be V1 right here, and it should be XORed right here. But if this was V3, I actually don't know that it's called V3. It's just some random number. But I know that like this XOR doesn't come from the output of this XOR right here, but I wouldn't know where it was. And so now you're like, okay, well, I know this one's bad, so I need to do some searching over here to find its other bad partner. And that's where I was like, oh, but it could be outside of the thing. And so I actually don't know. Like, I know that this one is wrong, but I don't know what it's like pairing is, like what it's wrong with at that moment. And that's what actually led me to doing these loops is I was like, I actually don't know what its pair is, but I do know that it's wrong. And so if I just keep track of the ones that I know are wrong, eventually I will find 8 of them that are wrong and I'm done. Like this one was meant to spit out. It doesn't do that right yet, but it was meant to spit out when I was doing this work, this one and this one, a result that either that specified here is the, it was actually panicking at the time, I think, but it was like meant to spit out like here are the 2 that are wrong from this adder, or here's the 1 that's wrong from this adder. You could probably still do that in another way, but as I was going through, I'm like, I really just need to think about it as when I'm trying to solve the problem. When I'm trying to say, is this adder correct? I just need to ask myself, does the initial XOR output to something valid? Does the second XOR output to a Z bit? And then I can just so I just ask myself those questions. Is this one consistent? And if it's not, I just spit out what's not consistent about it. Then I say, is this one consistent? And if it's not, I spit out this. And then I said, is this one consistent? And if not, I spit it out. And after I got to that point, I got all of my 8 and I stopped, right? I think I only check these ones right here, because the one I was checking was like this part right here. And that got me my 8. And so I didn't finish checking this one or this one, but that's essentially what I'm doing here with all this stuff is eventually I'm saying which of these are incorrect. And eventually you'll get there, right? It made it easier for me to think about it, even though the code is relatively large. Again, I could probably make this more concise, and this will be a day that I'll definitely go back to. I've said that a dozen times, right? So I really want to find, though, someone who solved it. Obviously, some of these people found some cool tool libraries to like look at it. Where do I even start? Yeah, if you're not familiar with these gates, a question is like, how do you even start with this? Behind solving it non-visually, I mean, yeah, you may just want to try and solve it visually first, and that will kind of give you an idea of what's going on. That's what led me down like the adder and half adder stuff, is kind of mermaiding it out and saying, oh, I'm doing addition. Admittedly, we got lucky because it was just ORs, XORs, and ANDs, and so it quickly brought me to like these half adders and full adders. And here's the ripple carry. This is called ripple carry adder. This is what it's doing. And so I just looked at the mermaid and said, oh, does it look like this? But there's other ones. The problem with the other ones is they, here's the quantum adder. The problem with these other ones is like they're carry ones and they use other gates. Often they use like NAND gates and stuff like that. Maybe I can show you what one looks like. It'll show you. These diagrams are substantially more complex. Carry look ahead. And XOR or XOR. This one is not using additional gates. So it could have potentially been this one, which is kind of more complex, right? Anyway, but I just got lucky and I was like, oh, hopefully it looks like this, and it did, and that solved it. If you're not familiar with any of this stuff, though, like visualizing it is probably the best way, because I mean, mine looks so ugly. I need to fix that way too. 24 was just a mess for me. And so you can see that, I mean, it just doesn't look very good. I don't know how the other person got theirs. I did try and color them. I'm like, okay, can I visualize the XORs? So it's easier for me to kind of see like the XOR leading to the other XOR with like this intermediate variable. Anyway. How do you solve this if you don't know about any of this? This would be a hard day if you're not familiar and just not doing it visually. And so something like this is like learning about logic gates and adders is probably good. There's enough gates that I don't know if you can just like start switching values and see if you get to the results. Admittedly, ooh, this is interesting. I think I'd mentioned this earlier. If you can check this and make sure it's consistent. This is an easy check, the half adder. And then you can check that this XOR is correct right here, right? And that this XOR is correct right here. Then you only really have to check like this one, like these. You only really have to like swap these to see if you get to the right value. I think I mentioned that before. So you might actually reduce like the space of like just swap two wires and see if it works. That doesn't work though in the general case where the swap could be anywhere, right? So I don't know. This is sometimes people say, "Oh, I just give up on these days," and I understand. There's been years before where I just didn't know, and I kind of had to give up and say, like, I don't know how to solve this. In fact, if you look, you could probably see. It would be nice to go back to them. This is the int code, and I think I just haven't solved it because I want to do videos on these two. Is this one I didn't figure out? I don't know. Some of these I may not have. I may have just been like, oh, this is too hard. I'm gonna try something else and do it. So that's totally okay. I hope you understand that that's okay. So okay, I feel like I've talked about this enough. It was a very crazy day for me. Day 24 was a crazy day. It was wild to solve, but I got there, and so I feel like yay success. Sometimes it's just getting the right answer. Again, I don't know that my solution is a generalized solution, so take it with a grain of salt. I would love to see how you solved it. Did you do it? Do you have a better visualization or a better way to visualize it? I'd love to see that as well, if for some reason you're still watching after an hour and a half. So there you go. Thank you very much for watching. We got one more day. I've actually already solved it, and it's not a bad day, so you'll see that video coming out shortly as well. And then AOC will be over, and we'll move on to, I want to do some rewrites of some of these days and talk about them more in depth, and that's what will be coming up in some upcoming videos. So talk to y'all later.